Hello there. In this video, we'll be dealing with examples on one-sided limits involving the absolute value function. But first, recall that one-sided limits is a type of limit that is only concerned with the behavior of f as x approaches a from either the left or right side. Let's have this graph as an illustration. As x approaches a from the left, the value of f of x is represented by this limit here. Similarly, as x approaches a from the right, the value of f of x is represented by this one out here. Now that this is out of the way, let's dive into a little bit on absolute value functions. So absolute value functions are functions wherein the output value must always be positive. So for instance, say if we have, let's fix this one. Say if we have this Cartesian plane out here and we consider this line, assuming this is y equals x, so we have this line out here. If we try to make this absolute value, then we know that y must always be positive. So with whatever values of x you plug in here, y must always be positive. That means that at this values of x out here, y must still be positive out here. So what happens in here is that this one, we remove this one, and this becomes reflected out here. So this is the graph of y equals absolute value of x. Since in here, the value of y must always be positive or in the positive y-axis. So out here. So all the functions out here must be in this region. And so that is how absolute value functions work. And let's try to illustrate this in a better illustration. So this one. So this is the same one that we had earlier, but it's now well written or well drawn. So this is the graph of absolute value of x. And the key thing in absolute value function is that we can express this one in terms of a piecewise function. So that is, we can express this one as x if x is greater than or equal to 0, or negative x if x is less than 0. So where did this come from? Take note that if x is positive already, we won't have any problems. So it's just what it is. So we just take the expression inside. But if we have a negative value of x, say if we have negative 1, we still need to multiply a negative out here to make this one positive. So that is the idea behind this part out here. So this is the thing that we'll be needing in solving limits and one-sided limits on absolute value functions. So I hope you got this one. Let's now move on to the first example. In here we are given the limit of 3x plus 6 all over the absolute value of x plus 2 as x approaches negative 2. So before we start this one, feel free to pause the video so that you may try this one first on your own. Okay, so let's start. So first, take note that the absolute value of x plus 2 is equal to So we apply what we learned a while ago. So this is equal to x plus 2 if x is greater than or equal to negative 2, and negative times x plus 2 times if x is less than negative 2. So how did we obtain this one? Well, take note that at the point negative 2, this is where this expression becomes 0. So we know that from the left of it, the value would be negative, and from the right of it, the values would be positive. And indeed, if we try to take a value greater than negative 2, say negative 1, then we have here negative 1 plus 2, and we have 1. So this is positive. But if we take a value less than negative 2, then say negative 3, so we'll have negative 3 plus 2 is equal to negative 1. So indeed, we still need to multiply a negative value. So that is the idea behind this one that we obtained. And since we have a piecewise function out here, we know that at the point negative 2, since we're tasked to get the limit as x approaches negative 2, we'll be needing to consider the limit from the left and the right. Or in other words, we'll be needing to consider the one-sided limits as x approaches negative 2. So starting with the limit as x approaches negative 2 from the right, then what we'll be using is, so from the right of negative 2, so that is values greater than negative 2. So we'll be using this one. So we'll have 3x plus 6 over x plus 2. So we replaced the absolute value of x plus 2 out here with just x plus 2. Take note that upon solving this one, we have 3 times x plus 2 over x plus 2. So we can divide the x plus 2's out here, since we know that x is not equal to negative 2, since we're just dealing with values that approach negative 2. So when simplified, this is the limit as x approaches negative 2 from the right of 3. Since this is just a constant, we know that its limit is the constant itself. So that is the limit of as x approaches negative 2 from the right. So take note here that we applied factoring, since if we immediately plugged in negative 2 out here, we'll actually have 0 over 0. So if you don't know how to apply factoring and evaluating limits, I'll probably link that one around in this video. Okay, so continuing the process, let's now check the limit as x approaches negative 2 from the left. So from the left, we'll be considering this one out here. So we'll replace the absolute value of x plus 2 out here with this one. So we'll have 3x plus 6 over negative times x plus 2. And similar to what we did out here, we'll have the limit of 3 times x plus 2 over negative times x plus 2 as x approaches negative 2 from the left. We can divide the x plus 2 out here to obtain this one. And since this is just a constant function, again, the limit for this one is just negative 3. So as you can see, we have a limit from the right and the left. But unfortunately, these two aren't equal. Therefore, we can conclude that the limit of the original one out here must not exist. So that is the answer for our first example. So I hope you got this one correctly. Let's move on to the next example. We have the limit of the absolute value of 4x minus the absolute value of x minus 5 over 1 minus x as x approaches 1. Oh, by the way, feel free to pause the video. If I haven't mentioned it a while ago, feel free to pause the videos out here so that you may try these examples first on your own. So let's start. So in here, since we have two absolute value functions out here, we'll inspect both. So we'll have here the absolute value of 4x. So take note that this is equal to 4x if x is greater than or equal to 0 and negative 4x if x is less than 0. So again, this is just similar to the process that we had a while ago. For the absolute value of x minus 5, this is equal to x minus 5 if x is greater than or equal to 5, and negative times x minus 5 if x is less than 5. If you're quite unsure in here, you can verify that upon plugging values in these region, you can see that we'll really be needing to multiply a negative out here to make the value positive. So clear this one there. So since we are dealing with the limit as x approaches 1, the functions that we'll be using out here will be, for absolute value of 4x, we'll be using this one since 1 is greater than 0, and for absolute value of x minus 5, we'll be using this one out. Take note that in solving this one, we won't really be needing to use one-sided limits since the functions out here wouldn't really change at the point 1. Although here you might argue that as x approaches 1 out here, these value would vary since as x approaches 1 from the left, this one out here will be 1 minus say 0.99. So this will be 0 but positive. And as x approaches 1 from the right, and this will become say 1 minus 1.0001. So this will become 0 from the left or from the negative values. Although you can argue that one, you'll see later why we don't need to really be getting the one-sided limits out here. So let's dive into that one. So we have the limit as x approaches 1 of, so we just plugged in 4x this one and negative times x minus 5 in here to obtain this. And observe that if we simplify this one, we start by distributing the negative value out here. So we'll have 4x plus x minus 5, or when simplified, so combining these two, we'll have 5x and minus 5. So that is what we'll be obtaining. And take note here that we can factor this one. So we have 5 times x minus 1. But since we need 1 minus x, we still need to factor a negative value out here. So we have negative 5 times negative x plus 1 or 1 minus x. We'll have that. And in here, this is the reason that we don't need to get the one-sided limit, since by factoring we can cancel these two out. And upon canceling that one, we'll be left with negative 5. So this is just a constant out here. And so we can conclude that this one out here, since this is just a constant function, we can conclude that the limit for the given function is just negative 5. This out here is the answer for our problem. Just to reiterate why we don't need to get the one-sided limits when we apply factoring, since observe here that 1 minus x over 1 minus x, if x approaches say 1 from the left, then this out here will become 0 and like that. And since we know this isn't really 0, these are just values from the right of 0, then we know that this 2 will just be equal to 1. And similarly, if x approaches 1 from the right, so this will just become 0 from the left and 0. So this will also just become 1. So that is why we don't need to get the one-sided limit out here. But if you want to verify, feel free to check, and you'll see that the limit from the left and the right would be equal. So now, let's move on to our last example. We have the limit of absolute value of x squared plus x over x as x approaches 0. Again, you may pause the video to try this one first. Okay, so let's start. So this will be fun, I hope. So take note that the absolute value of x squared plus x, so we can't really see immediately how its piecewise function would go, but take note that x squared plus x is equal to x over x plus 1. Although it is not written here, take note that if there's an absolute value out here by a property of absolute values, we can write this one as absolute value of x times absolute value of x plus 1. So we'll try to inspect what the behavior of the values of x, what the behavior of this function out here as we go on through values of x. So take note that the critical point of x is 0 and this one is negative 1. Or in other words, these are the points wherein this function or these functions becomes 0 and shifts from negative to positive. So let's try to plot in these points. So we'll have here this number line. And observe here that upon plotting these points, we'll be dividing this number line into 3 regions. So that is what we'll be considering in this piecewise function. So we consider the first region. So at x is less than negative 1, take note that, so again, let's write this one instead. Take note that x is less than negative 1. X out here becomes negative, so we need to multiply a negative out here. Similarly, there, let's fix that one. And similarly, at x is less than negative 1, x plus 1 out here will also be negative, so we need to multiply a negative out here. So that is how we obtained this one. For the region in between, so let's write this again. Take note that x out here, for values in this region, x would still become negative. So we still need to multiply negative out here. But for x plus 1, take note that this region out here, in this region, x is already greater than negative 1. So therefore, we don't need to multiply any negative out here, since the value of x plus 1 would already be positive. So we just have here this one. And so we have this. And lastly, for x is greater than or equal to 0, these two would actually be positive already. So we just keep it as it is. And so this is our piecewise function for this problem. If you want, you can even simplify this part out here, since you can multiply the negatives and that will just give us the same out here. But we won't be doing that anymore. And so let's now dive into the limit, or getting the limit of this function. Take note that since we have here x is less than 0 and x is greater than or equal to 0, and we have different functions out here, we'll be needing to apply the concept of one-sided limits in solving this one. So starting with the limit as x approaches 0 from the left, so that is x is less than 0, so we take this function out here. So we replace this one. So we'll have here negative x times x plus 1 all over x. Since we are just dealing with values that approaches 0 from the left and not exactly at 0, we can divide the x's out here, and we'll be left with negative times x plus 1. And in here, we can plug in already the 0 out here without any problem, since this is just a polynomial function. So we have negative times 0 from the left plus 1, or when simplified is negative 1. So the answer for this one-sided limit is negative 1. Similarly, we do the limit as x approaches 0 from the right. In here, what we'll be using is this function out here. So we have x times x plus 1 over x, and by similar argument, we can divide the x out here. and we'll have the limit as x approaches 0 from the right of x plus 1. Since this is just a polynomial function and we won't have any problem again, we can plug in 0 out here. So we'll have here 0 from the right plus 1, that would just give us 1, and so the limit for this one is 1. And in here, again, observe that even though getting the limits from both sides, we obtained a finite limit and a limit that exists. Since these two are not equal, we conclude that the limit for the original given is or does not exist. And this out here is the answer for this problem. So yeah, I hope you got that one right. The challenging part out here is obtaining this piecewise function out here, since it requires some analysis and observation. Yeah, I hope you enjoyed that one. If not, then let's just move on to the next one. Actually, this is just an exercise that you can work on. So in here we have the limit as x approaches 1 of absolute value of x plus 1 over the absolute value of x minus 1. So in here we have two absolute value functions. The idea here is similar to what we did in the third example. So you'll probably be needing a number line like this. And in here the critical point for this one is -1, and for this one is 1. So we'll have 3 regions, and you'll try to analyze how the function would look in this one. So yeah, that's it. I hope you enjoyed this one. So this is quite a long video, but I'll make sure to put the timestamps in this one so that you can easily go back to see what examples you need to focus or learn more on. So yeah, that's it, and that's all for this video.